Hello, in this lesson we are going to calculate the primitives of rational functions. Since this is our first session on this topic, we will only see some particular cases. The main objectives we aim to learn in this session are to know the primitives of rational functions and to properly make use of such technique. The prerequisites for understanding today's lesson include knowledge of simplifying fractions in a rational function and familiarity with the antiderivatives of powers and logarithms. What is a rational function? A rational function is simply a ratio of polynomials, with one polynomial in the numerator and another in the denominator. In this case, we have a polynomial p above and a polynomial q below. There is a very important result, at least in practice, which is the decomposition into simple fractions. What does this result of decomposing into partial fractions tell us? Well, it tells us that when we have a rational function of this form, px divided by qx, we can always break it down into a sum of a finite number of functions, f1, f2, f3, up to fn. Typically, this finite number is 3, 4, 5, or 6, usually not many more. These functions are referred to as simple or partial fractions, and they come in various types. What types, you might ask? Well, they can be a polynomial. In case of these being a polynomial, they would always be the first function, and there would be no more polynomials, only a single polynomial at the beginning, and that's it, the f1. And given a polynomial, we do know how to calculate its primitive. Let's observe now from the formula we have written that if the function of x is decomposed as f1 plus f2 plus fn, whenever we calculate the primitive of f, thanks to linearity, it will be the same as calculating the primitive of f1 plus the primitive of f2 plus the primitive of fn. Therefore, if f1, f2 and fn are simpler functions to compute primitives, they will allow us to compute the primitive of the complicated function of f more easily. Then, in the case of the function of 1, which would give us a polynomial in any case, it is quite simple mainly because calculating the primitive of a polynomial is standard. The second type of function that can be found is this kind, from x minus a, and this kind of functions are called logarithmic. The primitive of these functions is a logarithm of the denominator, except for the constant. The third kind of function is exactly the same as the first one we have seen, but in this case the exponent, in other words the denominator, is raised to an exponent different than 1, 2, 3, 4. In these cases the integral is not difficult either. It is no longer logarithmic, it is of the power type, but it is standard as well. And the very last type that can appear in these decompositions would be written the following way: a, x plus b above, a polynomial of degree 1, and below a polynomial of degree 2 raised to a certain exponent, where the polynomial a, x squared plus bx plus c has no real roots, it has its discriminant negative. In this session we are going to focus only on studying what happens when the functions that appear are of type 1, 2 or 3, just for simplicity's sake. Let's see all this in a practical example. Here we have an integral, a polynomial above and a polynomial below. As we can see, the expression is quite ugly to say the least. Let's resolve this by using the decomposition into simple fractions. The simple fraction decomposition tells us that this whole function decomposes as the sum of these three: a polynomial x plus a fraction 1 divided by x plus a fraction minus 2 divided by x minus 1 squared. We've chosen this specific example just so that you get to see the three different types we were talking about. Well, once we have reached this point, the moment in which we use the decomposition into simple fractions, which is a simple yet laborious step, we proceed to calculate the primitive, taking into account that the integral of a sum is the sum of the integrals. And that's the reason I'm able to divide this integral into three different ones: the integral of the first, the integral of the second, and finally the integral of the third. The integral of the first is very simple because it's x. Therefore it would be x squared divided by 2. The integral of the second is exactly the logarithm of the absolute value of x, which means that it is an immediate one, both would be immediate. And in the third one, the minus 2 remains, and if we observe the 1 divided by x minus 1 squared, it's actually x minus 1 raised to the power of minus 2, which is multiplied by 1. This 1 is the derivative of the function enclosed in parentheses. Therefore, we can also apply the rule for integrating power functions, which tells us that it will be x minus 1 raised to the power of minus 1 divided by the same exponent. In this case, we can rewrite it as x squared divided by 2 minus the natural logarithm of the absolute value of x, and now the integral of x minus 1 raised to the power of minus 1 divided by minus 1. In this case, the exponent and the denominator match perfectly. Finally, once we have done the last integral, we must add the constant of integration. It is more convenient to add it at the end, in order to avoid problems. Once we have reached this point, the only thing left is to simplify. X squared divided by 2 stays as it is, the logarithm stays as it is, and for the last expression we lower the x minus 1 back to the denominator, and we would end up having plus 2 divided by x minus 1 plus c. Well, this has been the example. As you see, it is quite a complicated function. Luckily for us, it can be divided into different steps, and each one of those little faces contains way simpler integrals. What are we capable of so far? Now we should be able to calculate the primitive of most of the functions p of x divided by q of x, basically the rational functions. Thank you very much for attending.